So let's look at a scenario where we have a reference configuration x1, x2. And I have a little cube in the reference configuration. And I'm going to rotate that cube, or square in this case, in 2D. I'm going to rotate that cube about the x3 direction. So the x3 is sticking out of the board. I'm going to rotate it about the x3 direction, an angle theta. So my deformed configuration, maybe I should have used different axis color here, right? So my deformed configuration would be something like this. So in this case, I'm not actually going to strain the cube. I'm just rotating it. Okay, and if we do that, just basically through the direction cosines of the coordinates, right? We're going to build a rotation matrix basically so that we can express the little x1 coordinates in terms of the big x1s, right? And if we do that, we'll have that x1, x2, x3 is equal to, and I'm just going to go ahead and write it in matrix form, but it's cosine theta minus sine theta 0, sine theta, cosine theta 0, 0, 0, 1. That multiplies x1, x2, x3. Right? So, I mean, I just wrote it right in matrix form, but everybody know how I came up with that, right? I'm just looking at, you know, I'm trying to express x1 in terms of, little x1 in terms of big X1 and big X2. So I have here you know, the cosine of the angle. So, you know, this looks like here I'm just using the vector x and times something, some matrix times little x. But if you imagine that our little if you imagine that our coordinates over here were infinitesimally small vectors, then you'd have something like this times something, okay? And if we call it f, then it's our normal equation for the deformation gradient, right? But in this case, it's a rotation matrix. I mean, I specified it's a pure rotation, right? There's no strain. So we're just going to say that f equals r, okay? So if f equals r, let's look at what the green strain is, right? The green strain is 1/2 f transpose f minus I. So I have 1/2 r transpose r minus I, right? Any rotation matrix is unitary. What does that mean? No, that would be isochoric. But unitary in matrix, right, it's just that it means that every rotation matrix is always a unitary matrix. It means that its transpose is its inverse, right? So I could also write this as R inverse, because its transpose is its inverse, R minus I. What is a matrix inverse times itself? It's the identity matrix, right? So I have 1/2 I minus I, which is in fact 0, right? The 0 tensor, the 0 matrix, which is what we want, right? All we did was a pure rotation and evaluate something we called strain. And since I said from the beginning we're not actually straining it, we're just rotating it, then we hope it comes out to 0, right? All we did was rotate. Okay. Let's try the same thing for the small strain measure. So the small strain measure, remember, is like 1/2 grad U plus grad U transpose. And remember, F is grad U transpose plus I. Right? So we could solve that for grad U transpose. So grad U transpose is F minus I. Right? And grad U is F transpose minus I. Right? So if I then plug this definition to get, because I want everything in terms of F, because that's our, F is equal to R. Right? So I want to get everything in terms of F. So if I do that, plug that in, we'll have F minus I plus F minus I transpose. And that's equal to, if you work it out, 1/2 F plus F transpose minus I. So we can write the small strain in terms of the deformation gradient only. And then if I plug this into R, F equal to R, then I have that R plus R transpose minus I. And we want that to be 0. When is that 0? The only time it's 0 is when R equals I, right? If R equals I, there's no rotation. So if there's any rotation at all, that's non-zero, right? This is not equal to 0 for any R not equal to I. So if there's any rotation, even if there's no strain, the small strain is not 0. So just in case you didn't believe me, here's a little example, right? So here's my little cube, and I'm going to, up there are some slider bars that allow me to manipulate it, apply some deformation this way, that way, turn it. And here I compute the linear strain and the green strain. I know it's a little bit hard to see. It'll show up good on the video. Right? But if I give it a little rotation, I haven't strained it. A little rotation, the green strain is 0, and the linear strain is non-zero. So if you use the linear strain, right, you're computing a stress, with a constitutive model, right? Plug that strain into a constitutive model. You're saying you're stressing or applying forces to this thing by simply rotating it. And clearly you're not. Right? So, and it doesn't matter, you know, how much you rotate it. But, you know, if you apply a strain, now another thing you can notice is that if I apply a really small strain, well, it's hard to see, but this one is the linear strain is 0.009, and this one is 0.00904. So for very, very small strains, they're really close to one another. Right? But if I go on straining it, right, now this is 0.31, that's 0.35, almost 0.36. So for large strains, this is a more accurate measure. So this is from those nonlinear terms. You need the nonlinear terms. So, and then of course, even, you know, if you apply some strains, then rotate, you know, you still now like all four of these components are changing. Clearly, you know, so as I rotate it, you'll see these changing, and that's not.